Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Protecting Your Spectrum Investments in Today's Hostile Urban Jungle, presented by Anritsu. Our presenter today is Patrick Weisgarber, Business Development Manager at Anritsu. And helping with the Q&A section for today will be Mark Heimbach, Senior Product Manager at Anritsu. At this time, I'd like to pass the presentation over to Patrick.
Thank you, Kyle. As Kyle mentioned, I'm Patrick Weisgarber. I'm a business development manager with Anritsu for our benchtop spectrum analyzers and signal generators, and also our signal monitoring solutions. So why are we here? Well, the main thing driving the demand for the spectrum monitoring solutions is that global demand is growing exponentially. It's expected to increase sixfold just between now and 2019. So what does that mean? Well, spectrum today is crowded. It's very expensive as well. The cellular network operators worldwide have invested billions of dollars in purchasing the rights to use frequency spectrum. As an example, just this year, there was approximately $65 billion bid on the AWS-3 spectrum just in the U.S. alone. So carriers and other spectrum users need to protect their investments and their quality of service. And interference mitigation is one of the ways to do that. It's a top priority because you have to optimize your network performance and maximize the revenue from the network. And then finally, the exploding demand for more bandwidth is driving the need to identify and repurpose underutilized spectrum. So who needs the ability to monitor spectrum? Well, first of all, the operators and spectrum users themselves. So if you need to do coverage measurements and interference mitigation, so your cellular service providers, anybody involved in public safety radio, positive train control, wireless backhaul, satellite communication providers, and your television and radio broadcasters. In addition, you've got your regulators. In this country, the FCC is the primary one, but there are similar bodies worldwide as well. So anybody involved in policymaking and enforcement, anybody who needs to shut down illegal and unlicensed radio or TV broadcasts, and anyone who needs to just look for spectrum occupancy and utilization. And then security and defense agencies as well, where they need to perform espionage and counter-espionage. They need to do signals intelligence work. They need to do security at sensitive facilities, and they need to monitor for illicit broadcasts from places like jails or prisons where there shouldn't be any unauthorized devices. So why is spectrum monitoring needed? Well, first of all, you need tools to be able to discover and facilitate the removal of interfering signal sources. So any signals out there that are unwanted that can cause interference, they may be intermittent, they may be periodic, they may change in frequency. Your spectrum monitoring, you need to be able to spot and identify problems as they occur. You need to also be able to go back and capture and log data to document problems. You need to be able to go back and examine any patterns of activity. You need to be able to look at what types of signals have been causing problems. And then you also ideally can locate the source of those problem signals so that you can take care of them later. You need to detect illicit transmissions near sensitive sites such as airports, borders, seaports, military bases, embassies, prisons, utilities like nuclear power plants, things like that. You need to be able to characterize spectrum occupancy. So you want to look at the usage rate for whatever targeted frequency bands you're looking at. And then you also want to be able to use it to develop statistics for determining whether that spectrum is underutilized. And if it is, then you can decide if there is some potential for sharing that or repurposing that to a higher, to another application that needs that bandwidth. And then you also need to be able to enforce in compliance with government regulations. So what would make you think there's interference in your network? Well, first of all, you might see an increase in drop calls and data connections in certain sectors from a base station. Your users may experience poor service quality, reduced throughput or data rates. Maybe there's audio distortion. Finally, there's metrics in your switching equipment that might indicate that there's problems going on within the system. Next step is to go ahead and verify that there's interference. So you would deploy spectrum monitoring probes out there. So for a cellular system or a distributed antenna system, you could monitor all the feeds from your receive antennas to look for signals that don't belong there. For other types of systems, you might want to deploy probes and antennas across a wide geography to look at what's actually out on the air. Next step is to observe the signal conditions at each probe. You need to kind of establish a baseline. Well, first of all, you look for unusual signals or behavior that you don't expect. Assuming everything looks clean, you would use that as your baseline. And then based on that, you will go ahead and set up the sweep parameters and pass-fail criteria that are correct for each of those probes, so that anytime those pass-fail criteria are violated, that's something that you want to look into, but otherwise you want to kind of ignore it. So it lets you surface issues and kind of, you know, if you've got a whole lot of probes out there, you obviously don't want to be looking at each one all the time. It's impossible to do. You want to be able to look across a bunch of probes and be an indication, know that there's one or two that need your attention. So once you do that, then you would go ahead and initiate your spectrum monitoring and data logging. After you've captured a certain amount of data, or maybe you get a notification or an alarm, you would review the captured trace data and determine what kind of issues you might have there. So you'd isolate what's undesired on there by your spectrum shape, your bandwidth. They might tell you a little bit about what's going on with the signal. Is it broadband? Is it narrowband? Is it a CW type signal like a jammer? Is it bleeding in from an adjacent band? All those things can tell you about what's going on. Once you decide what kind of behavior is going on that's causing your interference, you can go back, and you should be able to go back and look at the historical log data to determine, does this happen only during the daytime, for example, or is it certain days of the week, or maybe some external event drives it. Maybe you've got around a stadium at game day, you wind up with more interference than you would otherwise. Or maybe if you're monitoring a port, when a particular ship comes in, there are transmitters on that ship that are causing problems with your network. So you want to look for patterns in the data that might reveal what's going on and where that interference is coming from. Then you'd want to look at correlating that behavior across multiple probes. You want to see how widespread is the problem. You want to know if it's a localized problem, only affecting a small part of your network, or if it is across a wide geography. Is your interference source stationary or mobile? And then you'd also want to be able to know, is the interference source, is it intentional? Intentional broadcast can include, intentional interference could include something like a pirate broadcast of TV or radio. Could be a modified CB radio that's overpowered or transmitting onto frequencies where it shouldn't. Or maybe there's a jammer signal out there that's meant to block cellular communications, like sometimes in schools or in concert halls or in churches or something like that. There may be jammers in place to minimize cell traffic. And then The other type would be an accidental interfere. So maybe the antenna on a base station, either a interfering base station or your own base station, is misaligned so that it's getting signals in that it shouldn't. Maybe a cable TV system is leaking, and that can be ingress or egress, right? If you're monitoring a cable TV system itself, there could be interference coming into the system. If you're monitoring a wireless network outside, then there may be a leak from the cable TV system, which would appear as kind of a broadband noise across a wide swath of spectrum. Another one that's becoming more prevalent with the use of DECT phones, digital European cordless telephone. Those are available worldwide, but they operate on different frequency bands in different countries. So, for example, an international DECT phone that's brought into the U.S. will transmit in between the transmit and receive, or the uplink and downlink for a PCS network here in the United States. So that can cause interference. So, that would be an accidental. Somebody's just bringing their cordless phone along, and all of a sudden it's causing a problem with the mobile network. The next step, now that you've kind of classified everything, you want to locate and mitigate that interference. So you want to estimate the signal source, the location of the signal source. You can do that by triangulation from multiple probes, but there are limitations to how well that can work. Unless you've got a line of sight from your interference source to your spectrum monitoring probe, you can have multipath problems where you've got reflections from buildings or metallic objects out there. You can have shadowing where maybe a hill is between you and the interference source, so it's blocking that signal, it's attenuating that signal. Then also, even if you've got a clear line of sight and you can localize that transmission to a particular building, if it's a skyscraper or something like that, it can be very difficult to determine the elevation of the interference source within a multi-story building. So you can use mobile interference hunting tools to pinpoint the interference source with some intelligent starting points based upon estimates from your signal monitoring system. Then finally, you take corrective action once you identify where that source is. So when you're evaluating a spectrum monitoring solution, there are a few criteria that are important to consider. First of all, you've got to have good performance in your hardware. You're trying to maximize the probability of detecting signals. You also want to capture adequate detail, but you also want to minimize false alarms. So the key specifications, first of all, frequency coverage. It's got to cover the entire frequency bands that you're interested in. It's also got to have very good sensitivity so that you can see small signals. Spurious-free dynamic range. Dynamic range is the ability to see large and small signals at the same time. So you might have close-in transmitters that can saturate your spectrum monitoring device that cause it to be blind to the smaller signals. So an instrument with wide dynamic range can see both of those. It's also important that it be spurious-free because you don't want signals that are generated inside of your test equipment to appear as interference sources, because then you're just wasting your time trying to track down problems that don't really exist. And then the last point is you want to be able to do very fast sweep speeds at small resolution bandwidths. Resolution bandwidth determines the fine detail and frequency that you can see with your signal monitoring solution. You want the fastest sweep possible to maximize your probability of intercept for signals that are transitory in nature. The second step is you want your system to offer a lot of insight. It's got to be able to automate your control and measurements. It's got to be able to let you know when there's a problem and save data that you can use to track down the source of it. And it's got to have investigative tools that you can use for tasks related to spectrum monitoring and for interference location. The next step, reliability, very important. The intention a lot of times with these signal monitoring systems is you deploy them and they're in places that you can't get to very easily a lot of times. They've got to work fail-safe under adverse conditions in isolated locations. It can be very expensive to roll a truck just to reset a failed spectrum monitor or to replace one because it failed in its environment. Also, it's nice to be able to remotely maintain and upgrade those units as needs evolve. And then finally, scalability is very important. You want to be able to do all of these things across hundreds of probes. A network, if you're looking at a big wireless network, either a cellular, a public safety radio network, you could have up to hundreds of probes out there that you need to be able to control and monitor and log data for over a long period of time, weeks and months of time, terabytes worth of data. So the system's got to be able to handle those kinds of data. It's got to give you tools that you can use to find the needle in that haystack, look for their patterns and trends, and then finally you want to have some flexibility in your form factor for different ways of deploying these probes out in the field and controlling them. So now we'll talk a little bit about Anritsu's new series of remote spectrum monitors, the MS27100A Series. So the product line consists of two models right now. The first one, the MS27102A, is the IP67 outdoor rated unit on the left. And then there are a couple flavors of the MS27103A on the right. Those are rack mount units. I'll talk a little bit more about the details of those. So the 27102A is IP67 rated, so it's dust-proof, waterproof. It's got brackets available for mounting on a wall or pole, leaving it outside for long periods of time. You can have two RF inputs if you want to, so that you can use that for covering a wider frequency range using multiple antennas, or you can use that for two antennas to provide directional, angular, or spatial diversity. That operates off of DC power and requires an Ethernet connection. And it's, again, made to operate in harsh conditions. The MS27103A is a rack mount unit meant for multi-sector base stations and for distributed antenna systems out there. So what you would do is you would hook up each of these inputs to a receive feed, and then you'd be able to just cycle through each of those and check each of one of those one after the other. They don't all work in parallel. They work one after the other. So you can have up to 12 or 24 inputs for this, work from AC or DC power. And again, it's meant for mounting in a rack that would be in a typical base station or DAS deployment. Common characteristics of these: they operate 9 kHz to 6 gig. They offer fast sweep speed, high dynamic range, a very good spectral purity, fast operation, nice wide bandwidth for instantaneous capture and streaming. It's got demodulation for audio, for helping to isolate what the source of interference is. They all have integrated preamplifiers, GPS receivers, and gigabit Ethernet, so it gives you high-speed communications. So there are three different primary modes of operation for these remote spectrum monitors. So you've got interactive spectrum analysis, and what this is showing is the ability to work from one workstation to a whole multitude of these probes that are out in the field. And the probes, in this case, it's generic. It represents any one of the models. They all work the same. It's just a matter of what form factor is appropriate for, for what device you're monitoring out in the field. So you can work with them interactively. You can control them via a regular instrumentation control language. In this case, it's Skippy. And then there's Anritsu has its own vision software that can be used to work with these as well. And I'll kind of go through each one and talk about the capabilities behind them. So if you want to go in and just quickly look at the status of a particular probe out in the field, all you do is you log into a particular IP. Each instrument has a web server in it. And with the gigabit Ethernet, it gives you very fast responsiveness, lets you work with the instrument as if you had a spectrum analyzer right in front of you on your workbench. So you can view, control, and measure from any device that has a web browser. These are just some of the basic capabilities that you would see. Again, if you look at it, it looks just like any other spectrum analyzer, except the spectrum analyzer may be somewhere halfway around the world. So you can look for limit violations. You can look at a spectrogram, and the refresh rate on this is very fast. The spectrogram actually moves very quickly, so you can see how that signal changes with time. And then finally, the last one shows the sensitivity of the system. Sensitivity lets us see very small signals. So with Skippy, why would you want to use Skippy? Well, a lot of times you want to do, and especially in security agencies and things like this, they want to use their own algorithms. They don't want to share them with anybody. They want to be able to do exactly what they want to do when they want to do it. So they can connect anywhere from Ethernet. They can control the analyzer, get any traces and data back, digitize IQ data if they want to do further analysis, measurement results, everything else directly via Skippy commands, which are text commands that are sent back and forth across TCP/IP. And then there is the Anritsu Vision Monitor software, which was introduced at the same time we just introduced the new signal monitors. So what Vision Monitor is the central piece of the software, and what it does, it gives you the ability 24/7 to consolidate your spectrum monitoring across thousands of probes. For every channel of every probe, you can set an independent frequency range, resolution bandwidth, video bandwidth, reference level. You can turn the preamplifier off and on. You can set it to trace mode, so things like peak, minimum peak, peak plus, peak minus, average, RMS. You can set up max hold, min hold. All the things you can do with the regular spectrum analyzer, you can do independently per channel using this software. And then you can also set up a pass-fail limit mask to alert the user in case of something that happens that you're not expecting or that you want to capture. It's got a 30-day plus trace history database for each channel. So every channel has its own database, and it's consolidating the data from many of these channels. So you can have, again, like I mentioned earlier, terabytes of data captured by this system and easily accessible and searchable for certain problems. Data analysis tools, you can go back and replay traces from any desired set of probes. So you can click through the entire history of every trace that was captured from this thing with very fine granularity. You can identify your patterns of interference, looking at what bands, how often, whether they're fixed or mobile. You can estimate interference location if you have visibility with more than 3 probes of a given signal. And then you can also go ahead and generate reports. You can either do that on a per incident basis or on a daily, weekly, monthly basis, depending on what users need to see what data. The functions. So I told you this is kind of the hub of all our capabilities. So I'll start in the upper left there. So it gives you the ability to go ahead and edit your probe information and scan settings. You can see how it's got mapping built into it. So that with the GPS receiver that's in each of these probes, it can detect real time where it's located. So you'll be able to program it in and say, here's where it is, but it can also auto detect for you. You've got the ability, let's go around clockwise. You've got the ability to, with historical data, you can synchronize and go back, scroll through the history from a whole series of probes simultaneously and all synchronized. So the same trace corresponds to the same period in time for all of the different channels that you say you want to see. You can see the reporting down there in the lower right. And then finally the lower left, it's a pretty powerful capability. You've got the ability to edit the limit lines for a given channel or for the entire set of channels and probes that you're looking at, and then apply those limit lines retroactively to search through the data. So if, for instance, you get a failure, an interferer you didn't know to look for ahead of time, but you see it, you can go back and set up a condition that causes a failure with your limit lines, and then you apply that retroactively. You can see all instances where that signal popped up. So if you look at the display there, let me see if I can highlight this. So if you look at this big signal right here, right, you can see this pops up here through the limit line. If I didn't know it was there, I could set up a real narrow limit line focused right only on here and ignore everything else. You can see down in the spectrogram display here, if you look here where this line is across, this one, these are all areas where that signal popped up. So if I can go back and correlate timing-wise with that, and I can go back and correlate with other probes, it can give me information about what's going on, where that signal came from, and what happened. Okay, and then finally, there's the Vision Locate software, which I mentioned. If you've got the visibility of a given signal by 3 or more probes, we've got the ability to estimate, based on the power of arrival, we estimate where that transmitter is. So you would pick the probes you want and you can see the red marker line on here. You put that red marker line on the signal that you're interested in, and then it will, based on where you've told the system the antenna's pointed and the GPS location of it, and based on the received power, it can estimate where that signal's coming from. But like I said, that can be fooled if you don't have a direct line of sight into between the interferer and the signal monitoring system. So let's talk a little bit about our mobile interference hunting capabilities. So the important characteristics of a mobile interference hunting solution. Well, first of all, I think, for a value point of view is you're not doing this all the time. You want the spectrum analyzer you use to be usable on as many other applications as possible besides mobile interference hunting. So the things you care about for mobile interference hunting are low noise floor and high dynamic range, just like on the spectrum monitoring. But you also want tools like spectrogram demodulation. So demodulation means you can go out and where there's an interferer, it can demodulate that to figure out what type of signal it is. Is it LTE? Is it GSM? Is it a P25 land mobile radio? Is it a television signal? All those things are important to know. Signal quality analysis. So if you're working you're working on a network, you want to know, for my desired signals, right? My transmit signals, are they good quality or not? I want the spectrum analyzer in this to be versatile, because probably mobile interference hunting is a very small percentage of time that you're actually working with this. So you want it to be a very good spectrum analyzer. You want the antennas to be compact and portable so that you've got discretion when you're interference hunting in populated areas. So you don't want to be driving around the neighborhood with a, in a van with this huge antenna off it, because you'll get all kinds of calls into the police and everything else, and conspiracy theorists and everything. And then you also want it to be easy to transfer from one vehicle to another, so that you're not locked into one user or one vehicle at all times for interference hunting. The system's got to be easy to use, because again, you're not going to be using it all the time. It's got to be something that you can very quickly set up and start rolling when you get an alarm, because you want to capture that interferer as quickly as you can, so that it doesn't, first of all, so that you get your network up to full capacity again, but also because those interferers can come and go. You might have a limited time to respond. It also shouldn't require an inexperienced technician to operate. You should be able to hook it up and go without having to retrain every time you want to use it. And then last, it's got to be able to identify most types of interference signals you might run across. So cable TV or multiple multi-emitter signals, things that are periodic or pulsed, signals that are hidden in your LTE uplink bands, the ability to look at wideband, narrowband, and modulated signals, and also things that drift in frequency. So here is the Anritsu mobile interference hunting system. So it consists of one of our standard handheld spectrum analyzers. We've got a whole range of models that can be used with this. There's one antenna that we can use for it, that we recommend with it. It's got combined RF and GPS. It's very small, magnetic mounted, omnidirectional. But you can use this with any antenna. It can use separate RF and GPSs. It can use any other antenna that's tuned to the frequency bands that you need. This just happens to be one that is very commonly used for when you're working with cellular systems. The software itself, it runs on Windows tablet or PC. So you can see it mounted right here in the vehicle up on the dashboard. It's designed to automatically identify and locate your interference sources. And if you look on there, you'll see it's got a map display. The map will display on there, and it'll be picking up signal, and it'll actually direct the user where to drive to zero in on that signal. So you'll be going down the street, and it'll say, okay, turn left here. Okay, turn right there. Okay, turn right again. And by doing that, it's kind of taking different readings, taking different measurements to help zero in on that interference as quickly and efficiently as possible without forcing the user to pay attention to it. So the voice prompts are very important here because it lets one user operate the system safely without assistance. Finally, once you've driven around and again, you're even closer. So we've got kind of three levels of granularity in interference finding. The first would be using a spectrum monitoring, where you've got probably because of the likelihood of a direct line of sight between the interference source and the signal monitor is pretty low. So it's going to be a pretty wide range of error, circular probability of error for that. The mobile interference hunter will get you very close, but again, when you get around a building, a multi-story building, you may not be able to isolate to which floor it's on. In fact, you probably won't. So at that point, you can use our handheld system to do that. So we've got an interference hunter. You can see the little Star Trek thing that the guy's holding. It's got an antenna mount below, and it's got an integrated preamplifier for good sensitivity. It's got an electronic compass and GPS in it, and it works with interference mapping software in the handheld spectrum analyzer to let you zero in very precisely on where that interference is coming from. So you can use a variety of antennas depending on what you need. The log periodic, as you can see, has a wider beam width, so it's less directional, but it's also got a wider bandwidth, so it can see a wider range of frequencies. Where if you use a Yagi antenna, you'll need a variety of those because they tend to be very narrow band, but they're extremely directional, so they can very quickly pinpoint the direction where the interference is coming from. And that's all I have. So I guess we'll open the floor for questions.
All right, great. Thanks, Patrick. We've had a few questions come in, and again, anyone, if you have any questions at all, submit them via the control panel, and we'll get to them as best we can. Okay, so the first question we had, Patrick, is why are the 3 spectrum monitors needed to do geolocation of the interference signal?
Well, because you're looking at a power of arrival there. If you have a single monitor, first of all, let's assume just for now we'll assume an omnidirectional receive antenna, so it can get power from any direction. If we have one probe, we can't tell anything about direction. All we know is we've got a signal. If we have 2, then we know between the 2 probes, based on the power, we know that there is kind of an arc across which, or actually it would be a straight line in between those 2, well, not necessarily in between, a straight line upon which any interferer can be, and the third one is needed to get your X and Y zeroed in on that. Does that make sense?
Yeah, I think that answered the question. Next one we got in was...
Like,
oh, sorry, go on.
It's basic triangulation.
Yeah, that's what I was thinking. Next one we had come in is, what is the power dissipation of each spectrum monitor?
Each spectrum monitor is around 10 watts. So I believe that can be driven by most solar panels or whatever. It doesn't generate much heat. They are both fanless. They don't generate much heat, and they can be powered from a pretty low power source.
Okay, next question we had in was, what is the isolation of the RF ports in both the MS27102 and the MS27103?
I don't have the data sheet right in front of me. I don't know if Mark has. I'm sharing my screen. Well, let me see if I can get to it without.
Patrick, I can probably help here.
I can look that up while we ask the next question.
I think Mark may have it.
Yeah, it's about 35 to 40 dB of isolation, depending on frequency. So I say in the neighborhood of about 35 dB isolation.
And is that for both units?
Yes, it is.
Okay, thank you. We had another question come in asking about TDD and FDD interference. Can you go a little bit more into that as into how those systems are not GPS synced?
Yeah, it doesn't really need to be GPS synced for TESCOM. We can, well, first of all, we're doing spectrum analysis at the most basic anyway. So FDD, TDD, their spectrum will be the same regardless. If we want to demodulate, we can also demodulate without GPS linking. So it doesn't really matter if they're GPS synced or not. The GPS in this case is used for locating where the monitor is. So if we're out in the field and we're mapping and we want to do location finding, we know precisely where that device is located. It's also used for providing a very precise time reference when we capture IQ data from signals we're detecting, so that it will let us do time of arrival analysis as well, time difference of arrival as opposed to just power of arrival analysis for geolocation.
Okay, great. Next question we had in is, why are government regulators interested in spectrum monitoring?
Well, government regulators, there's a couple of answers to that. First of all, all with all the revenue coming into the FCC and and regulators worldwide, number one, they want to find spectrum that is not being used all that much, because maybe they'll put it up for auction and make more money off of it. Secondly, they want to, in order to maintain the value of that and to maintain compliance, they have to make sure that nobody is on that spectrum, on spectrum that they're not licensed to operate upon. So it's there for enforcement as well.
And Mark, did you have any comments as far as the government regulators' interest in spectrum?
Yeah, one of the main interference types of signals that the regulators look for is FM broadcast. And the reason for that is that the FM frequencies sit adjacent to air traffic control frequencies. So in many cases, if someone is broadcasting too high, or if the broadcast equipment is not sufficiently tested, then there can be bleed over and interfere with airline frequencies. So it's a main public safety is a big concern among government regulators.
Okay, thanks. So it looks like we only have one question left. So that one is there a set of predefined limitation of interference for different networks in the monitoring console?
There's not, but it's easy enough to do. There's kind of a limits database that gets created as you create different things. So, when you do, if somebody's doing, testing a base station or a cell phone, and they want to make sure that it's transmitting compliant with HSPA, with the HSPA spectrum emissions mask, there is a defined mask for that. But those masks really don't apply very well over the air because of all the things that can happen to a signal between when it leaves the base station or the handset till when it gets to our antenna. So we don't have anything predefined for that, but what you would typically do is you would look for the level of signals and the bandwidth of signals for the particular carriers that you're using or for the bandwidth you're using, and you would go ahead and create your own mask. Then once you create that mask, you can apply it across whatever range of probes that you want to use it for.
Okay, great. That's about all we have for today. I want to thank everyone for attending today's webinar, Protecting Your Spectrum Investments in Today's Hostile Urban Jungle, presented by Anritsu. Again, our presenter today was Patrick Weisgarber, Business Development Manager at Anritsu, and helping on the Q&A today was Mark Heimbach, Senior Product Manager at Anritsu. Thank you, everyone.